I wanted to start with a local story. I was at Sainsbury's the other day, Sainsbury's local, and trying to be friendly. It's a beautiful town here in Chester, and I pointed in the direction of Wales, and I said, "Beautiful hills." And the clerk said, and I said, he said, "France." I thought, well, okay, I would have guessed Ireland because it's the only country that the UK borders on, but okay. And then he told me, no, they have nice hills. And I looked puzzled again, and he explained to me the Alps. And so I thought about this, and I walked to the wall, which gave me an opportunity to use my high-class graphics. Nothing? And I looked over at Wales, and I thought, who was that guy? Right? He wasn't wrong. France does have nice hills. You know, the Alps. But on the other hand, I'm looking out enjoying the view of northern Wales. Now, if you've been to one of my talks before, you know. You go to a conference, it's a good conference like this one, and you're a good programmer. In fact, you're a very good programmer. You write good code, you ship code, you have happy customers. You come to a conference and some guy says, you're doing it wrong. Now, I am using guy in the Paul Hudson sense, appropriately, gender specific. You know it's a guy, because he said you're doing it wrong. And you think to yourself, well, we need two things, and Paul talked about this. We need more speakers who aren't guys, and we need fewer speakers who are doing it wrong. And so now I'm ready to get to my real talk. And so let's talk about functional programming. We will do a live demo later. You will do a live demo later. But the point is, you aren't doing it wrong. I just want to play with some ideas. What you're doing is fine. You have OO ideas that have worked well for you. You're shipping apps. Everything is fine. It's just that now that we have Swift, there are things that we can do in Swift. Now, technically, there's nothing we can do in Swift that we can't do in Objective-C because they both compile down to the same bytecode. So we know that there's nothing possible in one that's not possible in the other, but Swift is friendlier to some types of things, and Objective-C is friendlier to other types of things. And so some of the things we're going to talk about might be new to you. They might not be easy. And so let me start with example 1. I want to create a set of integers, which I'll call an int set. It is really a set. I can create it like this, and you can see it compiles and runs. It's a keynote joke. It's primes. I create it like this. I say I want to create a set of things that contain 2, 3, 5, and 7. I have a 2 through 7, and I'm creating that by saying give me a range from 2 to 7. And once I have these two sets, I can work with them. I can ask, hey, does 2 through 7 contain 8? It doesn't. Does 2 through 7 contain 3? It does. I can take the union of two sets, 2 through 7 union the primes, or the intersection of two sets. I can find the difference, what's in one set but not in the other, and the symmetric difference, what's in either set but not in the intersection. I can add elements to one. I can remove elements from one. Int set is an honest-to-goodness set. And you think to yourself, so what? We've had set for years. And I want you to think about how int set is implemented because I've done it in a little different way here, just to make a point. There is nothing wrong with the way you're thinking, where you're storing the elements somewhere. I just want you to think about something different. And so my int set looks like this. It is an int set, which is a struct. It has a single property in it, and that property is a function. The only thing that int set contains is this function contains, which tells you is an element in the set. And honest to goodness, everything you saw can be built off of this. Union, intersection, all those things can be built off of that. So I can start with the primes and this 2 through 7. I've got to create them, and so I'm going to create my custom inits to do that. And so if I do one that has a range, I just have to tell you what this function contains mean. I have to define contains, which is a function from int to bool. And so if I'm between 2 and 7, including 2 and 7, then x must be such that x is greater than or equal to the lower bound. At the same time, it is less than or equal to the upper bound. Now we have a set 2 through 7. And if you want to define by giving me the elements in like we did with primes, 2, 3, 5, 7, well, there's a nice little trick when I define contains, and that is when you send in this comma-separated list, internally, Swift changes it to be an array, and so I can just ask, does that array contain x? 2, 3, 5, 7 contains 2, does not contain 8. So I've got sets. And you say, so what? Swift gives us sets. But look at this set, isn't that cool? Tough audience. Here's something I can do with my set that you can't do with your set. I can create a set that contains infinitely many elements. I can create a set that contains all the even numbers. It's an int set where the contains is defined as you give me an int and I return true if it's a multiple of 2 and I return false if it's not. And my set contains every even number. Doesn't contain anything, and it contains every even number. I'll show you. Give me a really big odd number, you're going to get false. Evens doesn't contain that. Give me a really big or really negative even number, evens contains it. Evens contains every even number. It is an infinite set. I can create the empty set. Big deal. That's a set that contains nothing. You say, here's a number. Is it in there? I say, nope. How about the set that contains everything? Sure. You give me a number, I say yes. And so this can do everything that our regular set can do, but it can also accommodate infinite sets. We're not going to try anything new, Daniel. We hate this. That's okay. I just want to say that as I use this, I have no idea that my implementation just uses a function. And so the rest of my team, they're not as smart as you guys. The rest of your team can't handle functional programming. They don't have to. They can just use these high-level methods that you've exposed to them. And these high-level methods can be as simple as, how do you have the union of two sets? You're either in one set or you're in the other set. Oh my gosh, it's almost the way we define it. How do you do intersection? You're both in one set and in the other set. And how is the complement of self? The complement of self is everything that's not in self. They don't have to know how this is implemented at all. They can look and see union, intersection, and complement mean just what they think it does. That's just a thought. You guys are rough in the morning. My only property is a closure. And I could do things I couldn't do. Now, my example 2 is a bit of a stretch. My example 2 is one that you're going to say, we don't like this, and I'm going to agree with you. Then why are you showing it to us? We have time. So we have a line. So this is a tale in 3 parts. A little flashback to your old love of mathematics. Y equals mx plus b. Some of you look at this and say it's wrong. We learned y equals mx plus c. Oh, it's totally different. Here's my slope. Here's my y-intercept where I hit the y-axis. I have y equals mx plus b. And as programmers, we can look at that and say, y is a function that depends on what m is, what x is, what b is. We could think of this as being y equals a function of m, b, and x. We don't do that, do we? We think, well, if the slope is 2 and the intercept is 3 and y is 5, I can evaluate that. I can plug in 2, 3, and 5, and I can get 13. Or the slope is 2, the y-intercept is 3 again, and x is 7 this time. I plug in 2, 3, and 7, I get 17. I did the hard part for you, the multiplying and the adding. But we don't really think of y as being a function of m, b, and x. Instead, we think, I'm looking at a line whose slope is 2, whose y-intercept is 3. I am fixing the 2 and the 3. Yes? I can wait till you agree with me. And so we don't think of y as being a function of m, b, and x. We fix the m, we fix the b, and we think of y as being a function of x. That's what you do with lines. You say, it's this line, I give you an x, what's the y value? You don't say it's all lines, I'll give you the m and the b and the x every time. That would be a drag. So y is just a function of x, and in this case, the function of x is the slope times x plus 3, 2x plus 3. You've just done higher order functions. That's all a higher order function is. It allowed us to go from a function of m, b, and x to fix the m and the b and just end up with a function of x. The way we do that in Swift is we say, line is a function, you give me the slope, you give me the intercept, and what I give you back is a function from x to y that has fixed the m and the b. Oh my gosh, we thought higher order functions were hard. No, you've been doing them since you were like 14. And so I return a function. I write it as a closure. Why do I write it as a closure? Because you don't want your colleagues to know what you're doing. If you make it too readable, they'll just pitch in. And this is I return, and the way we read this is I return something that takes an x, and it returns m times x plus b. That looks just like this. That thing is f of x equals mx plus b, or how we used to write it in math, we could write it as f, which takes x and maps it to mx plus b. In Swift, we put curly braces around that, so we don't have to name it. It's anonymous, and we replace that line with the word in. And now we have a function that takes an x and returns mx plus b. So there's my line. And once I have my line, I can create an instance of my line. I can create 2x plus 3 by fixing the slope at 2 and the y-intercept at 3. And that's just this guy that we played with before. And once you have your specific line, you can evaluate it for various x's. You can say 2x plus 3 of 5. I did it before for you. The answer is 13. Thank you. And I can do for 7 as well, and I'll save you the trouble. It's 17. I know that gets hard at that point. So my line is a higher order function. I create an instance of it. This becomes hard, though, because I can't add behavior to this. When I had my set, I could add intersection and union because my set was stored in a struct. So instead of this line being this thing that's sitting out here in space, one of the things I might want to do is put it inside of a struct, and I'll do it like this. I'll create a struct which I'll name line. Line will contain only a property, y, that takes an int and returns an int. And now I don't want you to have to initialize it using that funny thing we did for set, so we'll add our own initializer in there, and the initializer says, you give me the slope, you give me the intercept. I'm not storing the slope and intercept somewhere. I'm just giving you this line. Y is take an x, return slope times x plus the y-intercept. Wait, can you do that? Can I give you a slope and an intercept and you don't hold on to them? Isn't the law we have to do self.intercept equals intercept and self.slope equals slope? Nope. You've created y equals mx plus b where you've frozen m and b, and so, excuse me. Just for kicks, I want to add an extension. Do any of you people play with subscripts? So a subscript allows you to treat something almost like an array where you can index into it. And so this is just a cheat here. I'm going to add an extension with subscript. And the subscript says, you give me an x, which is an int, and I'll return y of x. Well, why would I do that? Because now I can create 2x plus 3 this way using my init. Man, that looks familiar, doesn't it? It's a line with slope and intercept, and I can evaluate it using my subscript. Now, there is a new proposal in Swift Evolution being voted on this week that will allow you to enter callables, and you can replace those square brackets with parentheses by defining a call method instead of a subscript method. Isn't that cute? You wouldn't even know the difference between what we did before and now. That could never get you in trouble. So we have the square brackets for now, but if you compare this to what we did before, our way of creating the line, instead of calling this higher order function, we're instantiating a struct, and we're calling it almost the same way. I'm feeling pretty good because behind it all is a struct that contains this line. Now, this is not how you would do it. You would do this. And I don't hate you for it. I'm okay with that. We get pretty far with this, and I have a hard time explaining to you why this would be better because, in fact, it's not. That, in this case, is just an alternate approach. So as my third example, I want to show you one that gets better. The third example is hard. You waking up for third example? The third example is state. There's a very famous entity called state, and we're going to use it in an example to generate random numbers. Now, the problem with most random number generators is they're random. Right? If you're a random number generator, give me a number.
42.
What is it?
42.
42 doesn't sound random, but okay. Give me a random number.
7.
Give me a random number.
11.
He's not testable. He's giving me a different number every time. And you're saying, yes, he's a random number generator. He's supposed to. Not in our world. In our world, a random number generator is going to give me a number and the next random number generator. And every time I ask that same random number generator, give me a number,
7.
and give me the next random number generator. Just point to someone else in the room.
5.
So I didn't ask you anything. We'll get to you in a minute. If I come back to you later and I ask you for your result, you're going to give me the same number, so remember it, and you're going to point to the same person. Don't move. If it's an empty chair, it'd be like a crash, right? So, the function looks like this. The function for a random number generator is I ask you for the next int, and he gave me 7, and he pointed to his neighbor and said, that's the guy you're going to ask next time. And so if I want to test it, I come back to him later, and I'm testing something, and go, what's the random number? It's not like this guy who was 42, then 11, then he was all over the place, because he's a classic random number generator. Nothing wrong with him. We'd love him to come back next year. I'm just not going to use him in production. So, the key to functional programming, what makes it easier to reason about, why we say, if you can, use a struct or an enum, not a class, why we say use a let, not a var, is the idea is, if I give you the same input, I want to get back the same output. I want to be able to repeat, so I can depend on you, and I can understand you, and now I can use you in a bigger context. And so that's this guy. So let's go back to our live demo. I told you we had a live demo. You didn't know we were in the middle of it. Live demo says, run, and you tell me your number, and you point to your next guy. Run.
7.
7, and there, if I say to him, run again, he's going to give me 7 again. So I don't use him the second time. The next time the user presses a button and wants a random number, I say, run.
11.
There's part 2 of that. You got to point to the next one. Okay? Run.
0.
And me. Fair? Fair? 14, that's how it works. Do you see this? From the user's perspective, they're pressing a button and getting the next random number the same way as with him. The difference is we can test it. And he's not any more random than this is. He's still using an algorithm and there's a seed somehow. So are we. But our algorithm and our seed are giving us the next one along the way. I know. This isn't the way they teach it in school, is it? So, there is a famous structure called state. State is generic in two things, A and S. Usually it is written S and A, but every time I've taught it lately, students tell me it's less confusing in the other order, so it's A and S. A is the int that you gave me back. S is the person you pointed at who's the next random number generator. And so state contains a single function. State takes the S and returns the pair A and S. And you go, oh my gosh, you look familiar. And you say, that's such a tired pickup line. If I could tell you how many times state has been tried to pick up that way. But let's look at state in the context of a random number generator. If A is an int and S is the random number generator, then I'm going to create this type alias and create this guy called random. A random int is just a state that gives me back an int and the next random number generator. And so this function starts with a random number generator, whoever the person was that got pointed at next. And when I said run, you thought I did that capriciously. I knew where we were going. When I said run, he gave me back an int and said, there's the next one. So when I create my first one, I have to define this function. State needs to know its run function, and its run function says, I give you the next random number generator, you give me back the next int and the next random number generator. So that's what we did as we walked around here. So let's do it in code, what we did here. I pointed at him, and I said run, and he gave me back a pair. He gave me back a number, and he pointed at his neighbor. And so I said to the neighbor, I'm going to use you the next time I run this. And he gave me back a number, and he pointed to his neighbor. So I used his neighbor and ran it, and I got back, and we kept going. Does it almost make sense? Yes. I got time. Okay. You know that we're never happy. You know that programmers, it's not like we solve a problem and then we get to spend our life like resolving that problem. We go on to the next thing we don't know. So what if instead of random ints, I wanted a random bool? I can't use these guys because they give me back ints, or can I? So let's take a little side trip. Let's talk about map. Oh, we hate map. Oh. Our other teacher said we didn't have to learn map. I have a function, to bool. I'm just the best at naming things. To bool, you give me an int and I turn it into a bool, and the way I do it is the way you might want to do it, which is even numbers are false, odd numbers are true. That's just my to bool method. So to bool of 5 is true, to bool of 6 is false, and now I want to say to bool of this array. Why not? Because to bool goes from one int to one bool. I can't put an array in here. It doesn't compile. Oh, so it's the compiler's fault. So instead what we do in Swift is we do this. We say array has a map function. And array's map function takes to bool which knows how to operate on a single int, and map says, take that to bool and operate on this array of ints, and I should get back true, false, true, false. I get back an array. Well, why didn't I just write a separate method that worked from an array of ints to an array of bools? Because we don't do that as programmers. We're not going to take every single method from int to bool and then rewrite it for arrays. We have this map which says, I'll do it for you. But that's not the only map we have in Swift. We have a map in optionals too. And so if I create an optional int, so 5 is an optional int, and nil is an optional int, and I take those optionals and I try to put it into bool, the compiler says no. Bool doesn't know how to operate on an optional int. Bool only knows how to operate on a real int. Fortunately, we have map for optional. And so we can take our optionals and map it using bool, and what bool does in that case is it looks at the optional and says, in the bottom case, you're nil, I don't have to do anything with you. You're a nil int, you are now a nil bool. And with the top one it says, oh, you're not nil? I look inside the optional and I see 5. I change 5 to a bool using bool, and I get true, and now I wrap it back up in an optional. So I went from optional 5 to optional true. And that's what map does for optional. So I have this function from int to bool, and I was able to say, so much for my build. I was able to say, I want a function from an array of ints to an array of bools, and fortunately, because array has map, I could use array's map to lift this function from a function from int to bool to a function from array of ints to array of bools. I want a function from optional int to optional bool. Fortunately, optional has map. I can use optional's map. Map to bool is a function from optional int to optional bool. Now, it might help for this next part, if you drank heavily, it might help for this next part if we look at this a little differently. And that is, array of ints to array of bools, this is the way we write it, but really it is syntactic sugar for this. Yes? It is an array generic in int, an array generic in bool. We write it with square brackets because we understand what that means. But sometimes it's good to back up and say, but what does it mean? And this here, int question mark, bool question mark, is just syntactic sugar for this. And the reason that's helpful is now perhaps we see a pattern. And we say, wait a minute, if random had a map, then its map to bool would take me from a random int to a random bool. That's where you're supposed to go, ooh. I'm not going on. Thank you. It didn't feel sincere, but I'll take it. Now, if you look back at the type alias, random int, random bool was my state of int with a random number generator, and my state of a bool with a random number generator. So I need a map for this. Now, we're going to look at map for this, get what you can out of it. Got it? Just kidding. What it returns, this map, what it returns is, you give me an int RNG. You give me one of these people. And I say to them, run. And they give me back an int and the next RNG. And I say, wow, we're close. I don't want an int in the next RNG. I want a bool in the next RNG. And then I remember to bool is a function that can convert an int to a bool. So I take that int they gave me back and I transform it using to bool. And once I've transformed it, I have my next bool, and so what I return isn't the next int in the person. I return that transformed next bool in the person. Got it? I'll take that as a no. So here's my bool generator. I take my int generator and I apply this map using to bool. So let's do our demo first. You're still the int generator you've always been. Run. 7, and he points to him. I hear 7, but I map, and so I hear 7, and I apply map to bool to that, and I say, okay, it's true, and there's my next one. And now I go to him and I say, run.
5.
Was that really your number?
Yes.
We'll have to debug this later. and you need to point to your next person. No. I know that. Usually people work with me in this. I hear his faulty answer, and I transform it to true again, and I have my next one, and I say? 0, and he's pointed at me. 0 is false, and I'm the next one. I was 14, and so on. So at each stage, we still are giving you ints, but map is transforming it. The same way you started with an array of ints, and the map for arrays transformed it to an array of bools. That's what map does for us in each one of these worlds. Map is a design pattern. I know a lot of people think of map, and the only one they ever think of is the one for arrays, but maps are everywhere. And so here's what we did. I ran. He gave me back a number. I transformed it to a bool. I used that next RNG to find the next number. He lied to me about the number. I went with it. I transformed it to a bool. I used the next one, and that was our demo. So, with arrays, I had a transform from int to bool, and so map of transform took me from an array of ints to an array of bools. In arrays, if I had a transform that took an int to an array of bools, then map would take each int and map it to an array of bools. I'd end up with an array of bools. And that's why we have Flatmap. We have Flatmap, so we flatten that out, and I end up with a function from an array of ints to an array of bools. For optionals, if I have a function from int to bool, then map takes me from an optional int to an optional bool. If instead your transform was a function from int to optional bool, if I map that, I get a function from optional int to optional bool. Optional. So Flatmap gets rid of one level. And now we're in state. I'm not going to show you Flatmap, but I just want to tell you it does the same thing, which is if instead of giving me a function from int to bool, you give me a function from int to the state of bool and RNG, if I map that, I get the state of a state. And I don't even know what that means. So I flat map it, and I end up with a function from the state of int RNG to the state of bool RNG. And where this really pays off is in recursion. Because you get into a function that every time you come around, it wants to wrap it in a state. What Flatmap is says, oh, no. One wrapping is enough. That's the voice that my Flatmap uses. Okay. So let's suppose I'm getting tired of going through this process, and I'm the one who has to say run, and I'm the one who has to say run. That's exhausting for me. I'm old. So I want to find the next 5 numbers. Are you prepared with your numbers? And with the next 5 numbers, So here's the function, and I don't want you to fuss about the details so much, but the idea is if you ask me for the next 5 random integers, then I'm going to do a recursion, and each time through I'm going to say, okay, here's 1 of them, now find the next 4. Here's 2 of them, now find the next 3 until I'm done. And so the idea is when I'm done, I will return this array of things that I've been accumulating. The stuff I have grayed out is details. It's there, but it doesn't matter. Just the yellow stuff says, when you're done, return this array that you've been building up over time. If you're not done, so when I asked you for 5, when I ask you to give me the next 5, he gives me the first one, I hold on to it, and I go, okay, now give me the next 4. And what I pass on to the next function is the number 4 and my array of all the ones that I have so far. And so look, next takes a number and it takes my array so far. But it returns the state of something. And so if I didn't flat map it, I'd be, every time I recurred through, be getting the state of the state of the state. It wouldn't compile. I'd be upset. We'd have to invent something like Flatmap. So we're building up this array over time. And the cool thing about this is there's nothing in this function that's telling me how to pass the state along. The state just sort of magically comes along for the ride. So let's do our live demo. I'm going to find the next 5. 7. 7. What's your number? 7 and 8 I'm holding on to. 0, 780, 780, 14, 780, 14, 12. I didn't explicitly pass on the state. They pointed to the next person. This is called the state monad. I know, monads are frightening. But one of the things about the state monad is it passes the state along. What would we do in Objective-C? What would we do in an OO language? We would have something somewhere that was mutable that we would be changing. We would be adding on to it and keeping track of who's the next guy and what's going on here. We would have a singleton somewhere. It's not that these things are wrong. It's just that in the absence of that, we needed another method to pass the state along, and this was something that they developed in functional programming languages like Haskell. So what did we learn? A, sleep in and don't go to the first session on day 2. B, and C, in each one of these cases, we had a struct, and the only thing the struct contained was a function. And what was pretty cool was, in each case, we had state. In the set case, we had all the contents of the set, but a function was the only thing that was contained in there. In the line, we had the y-intercept, we had the slope, we could calculate were they intersecting, were they parallel. We could do all sorts of things with it. The only thing the line contained was the equation of the line. And with the state, our example was random number generator, but once state kind of sticks with you, I keep talking about these like design patterns. And if you think of the design patterns you might know and love from the Gang of 4, things like visitor and adapter and observer, these things you find we give them names because we use them in many situations. That's what's happening here. This happens to be one of those design patterns for the functional side of things. So now, you can just tell your colleagues, thank you.
Does anyone have any questions for Daniel?
Or existential ones.
Cool. Let me just get a microphone down to you.
Emotional ones. Why do we bother?
So yeah, thanks a lot for this talk. And
You're just being nice.
yeah. Oh, I must say, I'm French, and I live in French hills and not the Alps. And they are nice.
That's a statement, not a question, but okay.
So my question is regarding your insets at the beginning that you show using only a struct. I find it really appealing. One question that I have for you is, how would you iterate over this kind of set?
I can't, and that's a great question. What I lose there is it is not conforming to collection. I can't do next there, and the reason is because it could be. So with ints I could. With ints I could create a natural ordering where I just look for the next one as I go 0, 1, -1, 2. There's a natural ordering of integers. If I use doubles, there's not a natural ordering. So if I'm restricted to things that are countable, I could, because I could define what next is. But in general, I don't conform to collection. It's a great question.
Okay, thank you. Thank you very much.
Next question.
If you could be any animal.
All good?
I just thought I'd help.
In that case, please can we show our appreciation for Daniel? Thank you very much.